Hi everyone, I'm going to introduce my work about the upgrade of vacuum ultraviolet spectroscopy system on the JTAC tokamak. My presentation will be divided into 4 parts. The first part will introduce the motivation and background of the VUV system and its upgrade. The second part gives the configuration of VUV system and an example spectra. The third part presents some details of upgradation work and its preliminary results. In closing, the summary is given. Here comes to the motivation and background. As with most high-temperature devices, the vacuum ultraviolet spectroscopy is widely used to study the impurity behaviors by observing the distribution of emission intensity and the shape of spectral lines in VUV region. They fulfill both operation and physics goals. They are used in impurity monitoring to ensure the stable operation and also used to study the physics of turbulence and particle transport. And transient responses is needed when it comes to experiments related to 3D physics and other dynamic processes. It put forward requirements to VUV spectroscopy system on JTAC for making high time responses and relating spectral information accurately to the virus phenomenon. The JTAC tokamak has a circular plasma cross-section, and its minor radius can be adjusted by limiters. The limiters and the tiles are made of silicon carbide-coated graphite. The materials of the vacuum wall is stainless steel, so there are abundant lines for the intrinsic impurities such as carbon, oxygen, silicon, iron, nickel, and so on, as shown in the table below. And then is the configuration of the VUV system. Here's the layout and composition of the system. A normal incident spectroscopy with the concave grating of 1 meter focal length is installed on the equatorial pole 13 of JTAC tokamak, and wavelength ranging from 30 to 300 nanometer. A horizontal slit located between the entrance slit and the grating is used for spatial resolution. The central line of the site tilts up to 8 degrees relatively to the horizontal plane, achieving the radial coverage of half plasma cross-section, including the last closed flux surface. In the previous system, a back-illuminated charged carpal device is chosen as a detector. This example spectral lines measured by the system in the range of 30 to 300 nanometer is shown in this page. The spectrum is made via merging the spectra produced by scanning the central wavelength shot to shot. It could be recognized that the lines mainly come from carbon, oxygen, and silicon ions. As is shown in the picture, carbon is the primary impurity in JTAC tokamak, which would be the best candidates for the impurity transport study. And then I will present some details of the upgradation work. The Doppler broadening and emission in the VUV spectrum is lower than in the visible spectrum. The improvement of spatial and spectral resolution always lead to the sacrifice of temporal resolution. To overcome this limitation, the system has been upgraded. The new detector system consists of a microchannel plate equipped with the electron-multiplying charged copper device to replace the CCD we mentioned before. The plasma impurity emission from the tokamak pass through the entrance slit and spatial resolution slit respectively, and then comes to the MCP. The invisible VUV radiation is converted into a visible phosphor emission, which are detected more easily. The emission propagates along the fiber taper and then be focused on the EMCCD by the lens assembly. The efficiency of the system is estimated according to the power ratio at the entrance slit and plasma shown in the first formula and the area element to the detector in the second formula. And finally, the outer power at the detector is given from the last formula, and it turns out that the efficiency of the upgraded system is almost 2,000 times as the previous system. Here's the structure of the VUV system on JTAG's tokamak. The MCP is the key part in the whole system. It installed with the photocathode and phosphor to work as a photomultiplier. The photocathode is coated with cesium iodide for its suitable response wavelength range from 1 to 200 nanometer. Besides, the linear detection efficiency of cesium iodide-coated photocathode is about 30% in the wavelength of 10 to 200 nanometer. And P43 phosphor ensures the time resolution for its relatively long decay time of a few milliseconds, which match consistently with the EMCCD. The MCP operates safely only under ultra-vacuum, so it accompanies with a high voltage supply and molecular pump. The optical path of the system needs to be calibrated after the installation. The detailed design of the alignment planes is shown in this picture. 15 rectangular apertures are opened on the plate and numbered in order. The heights of the apertures and the intervals between the neighbor apertures are compiled for easily recognizing the serial number with a partial image. Each aperture and the space slit determine a line of sight which passes through a fixed part inside the tokamak. By moving the measurement wavelength, we obtain the exact viewing position in the tokamak of each line of sight corresponding to certain aperture. The picture here presents the projection images at several central wavelengths, and the measurement region is deduced in the table. It will be changed in different wavelengths. The upgraded system is tested under the condition of stable discharge operations, and here shows some preliminary results. The upgraded system has many advantages. For example, the detection of stronger brightness of the spectral lines from carbon, oxygen, and silicon. They are not observed previously for their relatively poor intensity, and also the higher temporal resolution to 2 milliseconds make the transient response possible. In this picture, the spectrum lines of carbon-3 and oxygen-3 emission is considerable in very short time. Finally, the achievement of spatial resolution of 1 centimeter makes the upgraded system completely sufficient for detection requirement. Here's the summary of my presentation. The VUV spectroscopy system on JTAG has been upgraded to fulfill the requirements of high temporal and spatial resolution in the transport study of the modulated experiments. The upgraded VUV spectroscopy system increases an MCP with the cesium iodide-coated photocathode and P43 phosphor, which then be acquired by an EMCCD. The upgraded system is commissioned with the observation of some strong lines from carbon, oxygen, and silicon, and the temporal and spatial resolution of the upgraded system has achieved to 2 milliseconds and 1 centimeter respectively. And that's all. Thank you for your attention.